Design of long transmission line by using MATLAB Simulink. In this session, we can understand the how to design the transmission line, long transmission line by MATLAB Simulink. First, in this MATLAB Simulink, first we have to take three-phase source, three-phase AC voltage source, three-phase source. This is for source side, and also the source side one measurement is required. Voltage and current measurement, three-phase VI measurement is required. Three-phase source, three-phase AC source, and three-phase VI measurement. Sending end side, so that is called sending end voltage and sending end current can be measured by using this three-phase VI measurement. This is called sending end side. And similarly, receiving end side also one voltage and current measurement, VI measurement is required. That is called VABC, IABC. So this is for receiving end side. And this receiving end side, three-phase series RLC load we have to take. Three-phase series RLC load. Okay. So in this three-phase RLC load, by changing it can be changed possible to RL or R or any type of load. Three-phase series RLC load. So this is called three-phase series RLC load. And then in between sending end side and receiving end side measurement, there is a transmission line. That is called long transmission line. The long transmission line parameters are distributed. Transmission line parameters are distributed, not lumped. So physical representation, physical and transmission line. So we can't represent this is the resistance and inductance and capacitance. The all RLC parameters are distributed, not lumped. Okay. So that's why this distributed parameters line we can select from the MATLAB. So this MATLAB Simulink, by using MATLAB Simulink, by taking one problem, numerical problem, we can understand the long transmission line, voltage regulation and efficiency. Okay, sending end side voltage, power, current, and we can measure this receiving end side power, voltage, and apparent power also. And then by using the sending end side and receiving end side, we can measure the voltage regulation and efficiency of transmission. And then coming to the one example, here three-phase 60 Hz 500 kV transmission line. Three-phase 60 Hz 500 kV transmission line is 300 kilometers. Long transmission line approximately greater than 160 kilometers. Okay. So transmission line is 300 kilometers long. The line inductance is 0.97 millihenry per kilometer per phase. The line inductance is called 0.97 millihenry per kilometer per phase, and its capacitance is 0.0115 microfarads per kilometer per phase. Assume lossless line. That is called resistance is 0. And then next, the receiving end it is rated is 800 megawatts. The receiving end is rated load is called 800 megawatts and 0.8 power factor lagging at 500 kV. The receiving end side voltage load is there. No? This is load is rated at 800 megawatts and 0.8 power factor and lagging at 500 kV. And next, so determine, these are the questions. First, determine the sending end voltage and current, sending end current, and active power and apparent power. Sending end voltage Vs, sending end current Is, active power Ps, apparent power S. Okay, this is called sending end side. And the next, determine the percentage voltage regulation as well as efficiency of the transmission line. These are the questions regarding this problem. And then from this problem, these are the data. Inductance and capacitance of the transmission line is given like this. Inductance per kilometer is given as below 0.97 millihenry per kilometer. Inductance in the question is given like this, 0.97 millihenry per kilometer inductance, and capacitance is 0.115 microfarads per kilometers. That is called 11.5 into 10 to the power minus 9 farads per kilometers. So this is the L and C values, inductance and capacitance of the transmission line. Then coming to the Receiving end active and reactive and apparent power calculations. The receiving end active power is given as 800 megawatts. In the problem, receiving end active power is given as 800 megawatts, like this. Receiving end is rated 800 megawatts now. That's why receiving end and the active power is given as an example 800 megawatts. Similarly, the receiving end apparent power can be calculated by S is equal to power divided by cos theta. Power is equal to S cos theta. That is S is equal to receiving end side power divided by cos theta. We know power factor, operating power factor 0.8 lagging. Then 800 megawatts power divided by 0.8. That is called 1000 megavolt ampere. This is called apparent power. And this apparent power can be calculated in the form of angle, that is called, and also it is a combination of active and reactive power. S is equal to P plus JQ, active power plus J into reactive power. That's why, so this apparent power is equal to 100 mega volt ampere. That is can be by taking the angle also 1000 at an angle of cos inverse of 0.8. That is equal to 1000 into cos theta plus j sin theta. And then we will get active and reactive power, receiving end, active and reactive power and apparent power in the form of like this. 800 megawatts is called P. PR, that is called receiving end side voltage, active power, and receiving end side reactive power. 800 megawatts plus 600 megawatt. Okay, volt ampere reactance. This is called reactance, volt ampere reactance, megavolt ampere reactance, that is called QR. PR and QR. So PR is called 800 megawatts and QR is called 600 megawatts. This is called receiving end active, reactive and apparent powers. Then coming to the receiving end voltage and current. So the receiving end voltage is given 500 kV. In the data, according from this data, the receiving end voltage VR is equal to 500 kV. So the receiving end phase voltage will be V phase is equal to VL by root 3. This is called line voltage. Okay. The receiving end line voltage is 500 kV. Phase voltage is called phase voltage is equal to VL by root 3, line voltage by root 3. 500 kV by root 3, that is equal to 288.67 by kV. And next, the current per phase is given by I is equal to S divided by 3 into VR. S is equal to 3 times of V into I. S is equal to 3 VI. Then I is equal to S conjugate divided by 3 into VR. Here means conjugate is taken if the polarity from the sign of angle will be changed. Sign of angle will be changed. Here S is equal to 1000 MVA at an angle of 36.87. So conjugate is nothing but minus 36.87 by 3 into VR. VR is equal to here 288.675 into 10 to the power 3. That is equal to receiving in the current per phase is equal to 1154.7 at an angle of minus 36.87. This is called receiving in the current, receiving in voltage. Okay, phase per phase receiving in voltage and receiving in the current. The next coming to the sending in phase voltage and line voltage. From the long transmission line formulas, sending in voltage is equal to cos beta into L into VR plus J into ZC into sin beta into L into IR. This is called VS. And beta is equal to omega into root LC. Omega is equal to 2 pi f into root LC. By substituting the values of beta is equal to 2 pi f, that is called frequency 60 edges and under root of LC, that is L is equal to 0.97 into 0.0115 into 10 to the power minus 9. Then we will get like this beta 0.001259 radians per kilometer. And then beta into L is called, so we will get 0.3779 like this. And then characteristic impedance ZC is equal to under root of root L by C. By substituting the L and C, we will get characteristics impedance 290.43. So these are all values beta and ZC substitute here. Then we will get sending end voltage. Sending end voltage is given like this: cos beta plus L into VR plus J into ZC into sin beta into L into IR. So cos beta is equal to 0.9295 and L VR is called 288.675 at an angle of 0. Cos beta into L is called 0.9295. Okay, then similarly J into ZC is equal to 290.43 into sin beta is equal to 0.3688. Okay, then IR is called, this is called receiving end current. Then we will get receiving and sending end voltage by simplifying this 356.53 at an angle of 16.1 kilovolts. This is called sending end side voltage. Then sending end line to line voltage is like this: VL line to line is equal to √3 into VS phase voltage. √3 type. Line voltage is equal to √3 times of phase voltage. That is equal to √3 into phase voltage 356.53. By substituting here, we'll get 670.17.53 kilovolts. This is called sending end line voltage. The next sending end current. The sending end current is given by the formula IS is equal to G into 1 by Z into sin beta into L into VR plus cos beta into L into IR. Then IS is equal to G into 1 by Z. Z is equal to characteristic impedance 290.43 and sin beta into L is called 0.3688 and VR is called 288.675 into 7 to the power of 3 plus cos beta into L is called 0.9295 into IR is called 1154.7 at an angle of minus 36.87. By simplifying, and then the sending end current is equal to 902.3 at an angle of minus 17.9 degrees. This is called sending end side current. And then sending end apparent and active and reactive power is called like this: S is equal to 3 VI conjugate. S is equal to 3 VI conjugate and 3 and 2 V as phase, sending end side phase voltage is called 356.53 into 10 to the cube at an angle of 16.1 and I conjugate is called 902.3 at an angle of minus 17.9 degrees. The polarity changes by conjugate. And then S is equal to 800 megawatts plus J 539.672 megavolt ampere reactance. So this is called apparent power at this sending end side. That is equal to 965.1 at an angle of 34 megavolt ampere. This is called sending end apparent power. Then sending end active power and reactive power is called, this is called S is equal to P plus JQ. P is called 800 megawatts and Q is called 539.672 megavolt ampere reactance. Okay, so 539.672 megavolt ampere. This is called sending inside and receiving inside. Then apparent power 965.1 at an angle of 41.8 MVA. Then it's coming to the percentage voltage regulation. This is the formula for long transmission line. Percentage voltage regulation is equal to VS minus VS by cos beta into L minus VR divided by VR into 100. Okay. And then substitute here, VS is called 356.53 and cos beta into L is called 0.9295 minus VR divided by VR 288.675. Substituting this values and then simplify, then you will get 32.87% is called percentage voltage regulation. The next transmission efficiency. Efficiency is nothing but output power by input power, that is called receiving end power by sending end power. This receiving end power and sending end power both are same in this problem. That's why 800 by 80 into 100, the 100% transmission line efficiency. So okay, this is about some calculations regarding this our example problem. This can be simplified by using MATLAB Simulink. Okay. I'm already explained how to design each block in short transmission line. So here already designed the long transmission line is there. Okay. So from each and every block we can understand. This is called three-phase source. So in MATLAB, enter here three-phase AC voltage source like this, three-phase source. Okay. Three-phase source by writing in this drawing sheet in this MATLAB, the worksheet, then you will get like this. So in this, open this three-phase source and write here according to our requirements, according to some our problem. And in this problem, open right here, phase to phase voltage is called 617.53 kilovolts. From example problems, phase to phase voltage is called. So what is this phase to phase voltage? 617 point sending end side. This is called 617.53 VS. Okay. Phase to line voltage, this is called 617.53 kilovolts. Right here, 617.53 kilovolts. Here. And then phase angle of phase A, degrees is called 16.1. So we already calculated. This is called 16.1 phase angle sending inside. So this is called 16.1 kilovolts. Right in this, open this block, three-phase source. Open this three-phase voltage source block. And right here, phase to phase voltage is called 617.53 into e power 3. That's called, this is called kilovolts. And then phase angle of phase A is called 16.1 and frequency is called 60 Hz. Okay. And then disable internal. This is suitable for fault calculations. Your fault calculations are not required. So that's why disable this and then apply OK. This is called three-phase source. Okay. First take three-phase source from this worksheet, from the drawing sheet, from the library, and place here and adjust phase to phase voltage is called 617.53 kilovolts and phase angle is called 16.1 and frequency 60 Hz and disable internal. Okay, then it will be appear like this. This is called three-phase source. Okay, three-phase sending and side. This is called source, three-phase AC source. Then to measure this voltages, three-phase VI measurement is required. So right here, three-phase VI measurement. Right, like this, three-phase VI measurement. Three-phase VI measurement. Like this, it is open, three-phase VI measurement. Okay, three-phase VI measurement. That is called this three-phase VI measurement. Connected three-phase VI measurement, A to A, B to B, C to C. And then this is called three-phase measurement. Similarly, receiving end side also, three-phase VI measurement is required. This is called three-phase VI measurement at a receiving end side. So copy this and paste here. And this is called three-phase VI measurement at receiving end side. This is called three-phase VI measurement at sending end side. And the next, this is called three-phase RLC load. So right here, three-phase RLC load, right, like this, three-phase RLC load here, three-phase RLC load. Like this, three-phase RLC will be we get from the library, control R, and it will be rotated like this. Okay, so control R and press control R, and it is rotating like this. Understood? This is called three-phase RLC load. So open three-phase RLC load, and in this problem, there is given nominal phase-to-phase voltage is called 500 kilovolts. Phase-to-phase voltage is in this problem is given like this. Voltage is called, load voltage is called 500 kV. This is called 500 kV. Three-phase series RLC load is having voltage of 500 kV. That's why in this entire 500 kV, phase-to-phase voltage is called 500 kV. And nominal frequency, operating frequency is called 60 Hz. Okay, so that's why so nominal frequency is called 60 Hz. And next, reactive power is called 800 megavolt. Active power is called 800 megavolt ampere, 800 megawatts. Active power is called at receiving end side. Active power is called 800 megawatts. That's why you write 800 megawatts. We already calculated active power at receiving end side. Receiving end side, what is the active power? 800 megawatts. Already is given in data 800 megawatts of active power. That's why enter here 800 megawatts of active power. Then in inductive reactive power is called 600 megavolt ampere reactance. Megavolt ampere reactance. Okay. Reactive power, here reactive power is called Q. By calculating like this, the reactive power is nothing but 600 megavolt ampere reactance. That's why enter here and the three-phase series RLC load. Reactive power is equal to 600 megavolt ampere reactance. Then next coming to the measurement, this is called capacitive reactance is called 0. There is no capacitive reactance power. That's why here enter 0. Okay, this is called sending and receiving end side load and sending end side. Okay, and then this is called distributed transmission line. Distributed transmission line, and this right here distributed transmission line. Distributed transmission line. Distributed transmission line. And this first one like this, and then it will be displayed, and we will get library from this library in the drawing sheet. Okay, so like this, this is called distributed parameters. Okay, and open this the distributed transmission line. Here number of phases is called 3A, and the length of the transmission line is called 300 kilometers. The length of the transmission line, long transmission line, is given 300 kilometers. That's why right here, length of the transmission line, open this distributed parameters line, length of the transmission line is called 300. And then frequency of this RLC specification is called 60 Hz. Operating frequency is called 60 Hz. And the lossless line, that's why there is no resistance. The resistance per unit length is called right here 0, 0 in terms of square brackets. 0, 0, 2 times right here. And next, also given transmission line inductance is called inductance per unit length is called 0.97 millihenry. 0.97 millihenry. That's why right 2 times 0.99 or 0.97 first one millihenry and 0.99 millihenry like this. Right, inductance per unit length. The next capacitance of the per unit length of transmission line here farads per kilometer. So that's why right is 2 times 11.574 into nanofarads. Okay, farads per kilometers. So from this already this is from given that what is this capacitance is called 11.5 into 10 to the power minus 9 farads per kilometers, or 11.5 nanofarads per kilometers. That here in this already predefined capacitance per unit length farads per kilometers is asking like this. That's why that is converted into farads per kilometers. That's why 11.574 into 10 to the power minus 9. So farads per kilometer, right? 2 times. Okay, like this. This is called about distributed transmission line. This distributed parameters line. Okay, understood? First, take three-phase voltage, three-phase source, and place here, and open three-phase source, and write phase-to-phase voltage is according to our example 617 kilovolts, and then phase angle is called 16.1, operating frequency 60 Hz, and disable internal. This is called three-phase source. And then coming to the this is called three-phase VI measurement. So three-phase VI measurement, open three-phase VI measurement, the direct connected to your different A to A, B to B, C to C, like this transmission line, and here to your A to A, B to B, C to C, like this transmission line, receiving end side is called three-phase, one more three-phase VI measurement. And this is called three-phase load, three-phase series RLC load, and normal phase-to-phase voltage is called 500 kilovolts, frequency 60 Hz, and active power 800 megawatts, inductive reactive power is called 600 megawatt volt ampere reactance. Okay, and capacitive reactive power is 0. So like this, the transmission line is designed. Okay, sending end side, receiving end side. In between there is a transmission line, long transmission line. Length of the transmission line is called 300 kilometers. The length of the transmission line 300 kilometers. Number of phases is called 3, and frequency, operating frequency 60 Hz, and resistance lossless line 0, 0. That's why right here 0, 0 resistance, and inductance per unit length is called 0.97 millihenry, right? 2 times, and the capacitance per unit length is called 11.574 farads per kilometers, like right 2 times like this, and this is called our transmission line is designed. the next measurement point of. So VABC, this is called VABC, is take one RMS, right here RMS, like this, RMS, take RMS and place here, okay, and connect one terminal of RMS, this is called VABC, and the second terminal is connected to display. This is called sending end voltage. VABC, that is called voltage ABC, A phase, B phase, C phase, that is connected to first RMS and then display. Similarly, IABC, okay, so IABC phases, IA, IB, IC phase currents connected to the one RMS and RMS to display. Okay, so like this, VABC, VA, VB, VC can be measured by using RMS values in terms of RMS and connected to the display in this way. Similarly, current IA, IB, IB, IC to measure, connect this IABC terminal to the RMS and then connect to the one display, and it will measure the RMS value of currents IA, IB, IC. Okay, this is called sending end side. And also to display active power P and also reactive power Q, one three-phase instantaneous power is required. Three-phase, take this three-phase VI measurement, power measurement, that is called power measurement. Take this three-phase instantaneous, power three-phase instantaneous. Take this block and then place here. That block is called this three-phase power instantaneous. Don't enter another name, sir. So enter name like this, three-phase instantaneous, power three-phase instantaneous. Then only you will get this block from the library. Right like this, right like this only, power three-phase instantaneous. Okay. So VABC, so this is connected to the like this VABC of VI measure, sending end voltage. This is called sending end voltage. And this next is called sending end current. So sending end voltage and sending end currents are connected to the power of three-phase instantaneous. Okay, VABC to VABC, IABC to IABC. Then P, this is called active power, and Q is called reactive power for sending end voltage. So from P to take one display, connect here, and Q to also take one display, connect here. This display is called sending end active power. This display is called sending end reactive power. Okay, so this entire connection are called sending end side. Sending end current, sending end voltage. Okay, so from VABC to connect to one RMS and connect to the sending one display, that is called sending end voltage and the sending end current. And if you want to display the power and connect VABC to power instant three-phase instantaneous to VABC and IABC like this fashion. And it measures separate P and Q. It's measure the power and active power and reactive power for sending end side. So like this. Okay. So this is about active and reactive power. Then how to find the apparent power, that is called S is equal to VI. Okay. So take one product from the library right here, product. So like this product. Okay. Take from library, right, by writing this on the screen, you will get this element directly. Take one product. So product is called S is equal to V into I. This product input, one input is called VRMS and IRMS. One input is this called current, IRMS. And this input is called VRMS. After the IRMS, after VRMS, multiply VRMS into IRMS, okay, by using product block, okay. Then product block will multiply the V voltage, sending end voltage, and sending end current, and sending end voltage, like this. And then power is called S for three phase, 3 into VI, S is equal to 3 into VI. That's why one gain is required. Take gain and write here gain, okay, and then like this gain, open gain, and write here and on this gain here 1 instead of 1 write 3, and then okay, apply, okay, and then the display will be, the gain is called multiplied by 3 times. This is called gain. And then after compile, after run, you will get here apparent power. Okay. So this is about sending end side, measurement of voltage, current, and power, active power, reactive power, apparent power. By simulate, and then this results display like this. Sending end side voltage is current is called 901, 900, 900. So according to our calculation, the sending end current is called 900, okay, 900 amps. And the next sending end side voltage is called 3.564 into 10 to the power of 5. Sending end side voltage is nothing but here 356.4 kilovolts. Okay. So this is called sending end side voltage. And the next sending end power is called 8.023 into 10 to the power of 8. Okay. That is called 800 megawatts. Active power, approximately 800 megawatts will get active power. And the reactive power is called 5.34 into 10 to the power of 8. This is called sending end side reactive power. Okay, sending end active power and reactive power. And then next, these are the results. And apparent power is called 9.637 into 10 to the power of 8. 963 kVA or MVA, 963 MVA. This is called sending end side apparent power. So, okay, this is called sending end side. Then copy whatever the components sending end side measurements all like this, copy and paste for receiving end side. Okay, same blocks are required for measurement of receiving end power, receiving end current, receiving end voltage, and apparent power. That's why no need to design again, and then copy all elements and connect VABC, IABC on the receiving end side. Here VABC, IABC, receiving end side. So copy all these components, and only here. So instead of placing the sending end side, place receiving end side. All right, rewrite like this. This is called receiving end current, receiving end voltage. VABC is connected to the voltage. That's why you write receiving end voltage. It measures receiving end voltage. And next, this is called receiving end current. Okay, by connecting the RMS and the display to the IABC, then we will get receiving end current. And similarly, to get receiving end side power, so take one power 3-phase instantaneous, connect to VABC, IABC terminals of receiving and 3-phase receiving end side, and then it will be measured active power and reactive power at receiving end side. Receiving end active reactive power, active power, receiving end side active power, receiving end side reactive power. So measure like this. The same blocks are required at receiving end side also. The receiving end 7.967 into 10 to the power of 8. This is called receiving end side power. That is called 796.7 megawatts. It's called receiving end power, active power. And the receiving end reactive power is called 598.4 megavolt ampere reactance. It's called receiving end side reactance. And apparent power of receiving end side 9.965 to 10 to the power of 8 is nothing but 996.5 megavolt ampere MVA. So like this, sending end side voltage, current, active power, reactive power, apparent powers are calculated. Similarly, receiving end side also apparent power, active power, reactive power, receiving end side voltage, receiving end side current, receiving end side voltage can be calculated. Okay. Then next, how to find the regulation. So regulation is called Vs minus Vr divided by Vs into R for short transmission line. For long transmission line, this is the formula for regulation. Okay. Vs by cos beta into L minus Vr divided by Vr into 100. Okay. This is called regulation at receiving end side. So Vs we know 356.53. cos beta is equal 0.9295 minus VR divided by VR into 100. So here some small, this is called, we have to change. One constant is required to multiply 356.53. First, take one constant. That constant is called 1 by 0.9295, and this can be multiplied into 356.53, and then it is subtracted, and it's divided by 288.675, like this. So to find the regulation, first this is called first take one block that is called 0.9295. That is called cos beta into L is called 0.9295. Then this is called, take one constant right here, constant, and then place a open constant right here instead of 1. That is called, our according to our calculations, cos beta into L is called 0.9295. So the at divide terminals, at division terminals, okay, and this is called product terminals. So Vs into cos beta here, 1 divided by, this is called division, means Vs into 1 by this division 0.9295. Okay, Vs into 1 divided by cos beta into L is called this, we will get like this. Okay, 0.9295. This is called division symbol, and into symbol, that is called Vs into 1 by 0.9295, like this. After this, minus, and the next, what is this? After this, Vs minus Vr, na? So this term minus Vr is required. So that's why select subtract, right here, subtract, like this. Subtract, from this subtractor here, one terminal is connect here, this Vs into 1 by 0.9295. This Vs into that is another 356.53 into 0.9295 minus Vr. Okay, minus Vr, that's why. So receiving end side voltage, we know this is called receiving end side voltage. This is called voltage, and this is called current. Vs minus Vr by Vs minus, then after this subtract terminal, we will get Vs minus Vr. Okay, by Vr is also required. That's why, so from divisor, take divide, and then right here, take connect one terminal, that is called divide. This is called Vr. So here, what is the expression is nothing but Vs minus Vr divided by Vr. By Vr is also required. That's why here we have to take Vr. And then multiply into 100. Vs minus Vr divided by 100. So this constant into 100 is, we will get regulation. We'll come simulate, and then we will get 33.35% according to 32.87, approximately equal. Okay, this is about percentage voltage regulation. And then next, efficiency. How to find efficiency? Output power by input power is into 100 is called efficiency of transmission line. So that output power is nothing but PR, receiving end side, PS, sending end side. So here 7.967 PR, and PS is called 8.0. 7.967 is approximately 8. Here also 8. That's why efficiency 8 by 8 into 100. This is nothing but 100%. Okay. So in this way, the long transmission line can be designed by using the MATLAB Simulink. Okay, understood. That's it for long transmission lines.